Well, while this situates itself in the... Okay, great. Here we are. Well, I'm David Wessel, and actually my position here at the university is in the Department of Music, and I'm the director of a center called the Center for New Music and Audio Technologies, which is just nearby over on Arch Street, and we do work in computer music and so on. And I'm a musician. I use computers. And in fact, once I was asked, what instrument do you play? And I said, the computer. And of course, that leads to all sorts of things. So I'm really interested in the whole chain from capturing gestures, analyzing those gestures, doing a lot of computation on computers. And then we use the computers in the chain as well, and then diffusing the sound on speaker arrays that have large numbers of speakers. And so this looks like it's going to work fine. So I'm going to, I know that you've heard a lot about linear algebra, sparse, dense matrices, and these kinds of things. So I'm going to spare you some of that. But let me just say that those dwarves, those motifs, are everywhere in the music area. We do a lot of linear algebra. We do a lot of spectral processing, and so on. So that's really a big part of the kind of computation, underlying computation. In fact, if you were to look at the kind of motifs that we use practically all of them. Structured grids as well, because we like to do physical modeling and so on. But I'll spare you that today and talk about some other issues that come up in trying to make things run in parallel. Now, what's important to know as well, is this, are you, what the batteries? Maybe you can see that. Can you hear me now? Yeah. Okay. Here we are. There's play somewhere. See if we can get it all on the screen. Yes. Okay, let me just... All right. So I'll say a few words. These are these slides. I probably won't be able to get through all of them. Are you going to keep me on time? Or try. Okay. Good. So let me just say that as I was about to say, we have, in this musical field, we have a really insatiable appetite for computation. In fact, I actually carry, when I go to play concerts and so on, I go typically with 3 laptops that I'm running all at once, doing different kinds of jobs, and they're all linked together. So parallelism is already there, and I can't wait till we have, more cores on these things that we can take advantage of. Now, mobile devices are also magnets for developers, and of course we have the well-known iPhones and Androids and so on, and now the new iPad. And there, if you look, and you'll see just lots and lots of applications. And again, people are saying, "Oh, I wish we had more horsepower on these devices," and so on. To give you an idea of what's going on here, we have had for the last few years these music hack days throughout the world, and people are showing up, and we have professional programmers involved in writing low-level code. We might call these the ninja programmers. They're writing complex signal processing code and able to do things in C, C++, and on GPUs. And then at the other end of the spectrum, we have amateurs who haven't programmed at all, who are musicians who want to do some creative work, and they're learning to program in various domain-specific programming languages. And one of them that's very popular, I want to get to in a moment here, is this environment called MaxMSP. It's a visual programming language, and it's modeled after data flow things. You'd think it would be, let me say a few words about it. If you look at this, this is these are some sample patches here. On the left, you'll see this connection there made with a striped patch cord, and then you'll see these other links, these patch cords we call them, that are solid lines. Well, there are two different kinds of data that pass over these things. Over the striped patch cords, we have sample synchronous audio data. In other words, it's what we call sample synchronous data flow. And on the solid patches, we have asynchronous events that are bopping around and setting up parameters and that kind of thing. So this is a typical programming environment for someone getting their feet wet in this area. And you can write very complex and large programs with this. Now, you'd think that with these graphs, like structures, that we ought to get to parallelism pretty quickly. But at the moment, most of the languages of this sort, have not proven to be simple to parallelize. We're working on it. And I'm going to say a few words about that as we move through here. But this is a typical programming environment that musicians feel comfortable with, and these are highly productive environments. And we want to bring parallelism to them. And I'm going to talk a bit about the successes so far and the difficulties in doing that. So just say a few words about some of the applications. This is a loudspeaker array which has 88 speakers. Each of them is separately addressable, and it's used for something called Wavefield Synthesis. In other words, we're able to actually create a wavefront that looks like the wavefront that would be created by a real source and make that virtual source have a specific location that's fairly stable, and people can walk around it and hear this sound hanging out right in the air. This is of interest to a number of people. I was just up in the tele-immersion laboratory where we're going to be looking at this kind of synthesis as well. Well, it turns out that programming environment that I just showed you is very useful for controlling these arrays, and a lot of the signal processing has been incorporated into them. But you can see here that we've got a great deal of parallelism. Well, it's nice to have, traditional musical ideas enter into that, and so people have spent a lot of time doing notation programs. This is a very unique one called Notability, and it includes the computer parts. You can see start, bang, rev on, and so on. These are commands that this particular environment sends to this environment that I was speaking about. So here we've integrated notation as well. So those give you an idea of some of the patches. Now, from the patterns perspective, it turns out that these patches are really rich in what we would call pipe and filter patterns. We're patching together objects, we call them, in what really look like sequences that resemble pipe and filter. Now, the other thing that's really important about these languages is that they're component-based. In other words, the signal processing components and the event processing components that are become available are usually put into some sort of plug-in format. They're either the internal plug-in format for the language itself, or they use one that works in many languages. This VST plug thing, audio units, is Apple's standard, and so on. So what we can do is actually write parallel code for these components in using p-threads, which I'll talk about in a moment, and or OpenMP, and so on. And so these components can themselves be parallel processing entities. Now, the real challenge is to make those components work together. So you might have a sort of thread ecology, I like to call it, in one component that's in conflict with the threading ecology in another component. And so when you bring them together, you can have some real problems, and in fact have performance that just goes to hell. And in fact, sometimes you thought you've parallelized and got some improvement, but what you've really done is paralyzed the system instead. So we've got to watch about how these components operate. I'm going to skip over this for the moment, and just in the interest of time, and say something about the way these components, we're working on operating systems, and this component approach to parallelization turns out to be a natural for the tessellation operating system. I don't know, has that been presented? I think so, a bit in the course. So really, once again, composition of components is a key issue. So what I'd like to do now is tell a story about where we are with respect to this composition of components and talk about the difficulty that people are having with this now and what we need to do to fix it. So there's a very popular digital audio workstation which is called Ableton Live. It has over 700,000 users. So we're probably going to see 1.5 million in a couple of years, and it's DJs use this sort of thing. People are doing all sorts of audio production use it. Now it turns out that this MaxMSP environment that I showed you, this patching languages, allows you to write components for this language or this environment. It's not really a language; it's more or less a workflow situation. So it's very popular, very easy to use, very well aimed at mere mortals, you might say. And so you can write specialized code for that in this MaxMSP environment for this particular environment. Now, when you do that, things fall apart. So if you have the parallelism that is available in the Ableton situation turned on, you're going to use multi-core, and you have the parallelism in the MaxMSP environment turned on, multiple voices and so on, they bang their heads against each other. In fact, each of them tries to oversubscribe the thread resources and so on. So we need some kind of thread management system for this. And what the Parallel Computing Lab has come up with is something called Lithe. And it's a cooperative thread management approach, and it really helps this composition problem. So I'm going to show you some results we've got with this now, and I think you'll see that we're making some real progress here. We want real-time, reactive real-time in this thing. So what we did was we built a component or a plug-in architecture, we call it, that will run these kinds of components. We built it on top of Linux, and we can use the Linux-style audio component structure. We're using it in conjunction with FFTW, and in this particular system, we're doing a Fourier transform. In other words, we might be building impulse response reverberators and that sort of thing. And so we're going to do convolution here. In other words, we're going to do an FFT, multiply in the frequency domain, and then do an IFFT to get the data out. So we're looking at a system that takes audio in and gives audio out, but in the inner thing, there's some spectral processing that's going on. So what we did was we made implementations of this with p-threads, this double FFTW situation, this convolution program, with OpenMP, and with this cooperative thread management system. And here's what we got. Well, as the number of cores, we got the number of cores along the bottom axis. Well, it looks like OpenMP. Let's go down to just the number of context switches that occur. You can see OpenMP really requires a lot of management of content. In other words, there's just both of these threading environments are are trying to grab resources. And if we look at the top graph as well, we can see that the OpenMP implementation, we've got this is normalized execution time, so the lower the better here. So we can see that the OpenMP version is the worst, and up above, then next comes the pthreads version, and we get a real speed up with the Lithe, or cooperatively managed threads. So this is really critical. Now, to date, the operating systems that you're used to, let's say, not necessarily, I haven't gotten used to Windows, but Windows, the Mac OS, do not provide for this kind of thread management. In this case, we put this as a thin layer over the top of the Linux system. But we do know that inside of Intel and inside of Microsoft, they're working on this kind of cooperative thread management issue. It's absolutely critical to get multiple different kinds of threading ecologies to work together. And that's the message I want you to go away with. Just don't think that you can combine things. For example, if you have TBB, the thread building blocks, and you have, and you have the MKL, parallel arithmetic library, and then you have OpenMP. Well, if you try to use them together, machines come to their knees. Each of those has its own threading. Each of those libraries has its own threading ecology and gets in the way. So the way to get around it is to use some kind of cooperative thread management. So I'm going to bring this to a close right now, and that's the take-home message. Manage your threads carefully, and don't believe that you can get away without doing it, because things will conflict with each other. Thank you. Any questions? Okay, Leo, you're next.